Hello, my name is Brad Fields. I'm the Senior Director of Manufacturing here at Bloom Energy. This is our brand new state-of-the-art stack manufacturing facility in Fremont, California. This is a purpose-built 165,000 square foot manufacturing facility specifically for fuel cells. We started producing the first components in here in December of this year and scheduled to build out by the middle of next year. Most of our fuel cell manufacturing today is down in Sunnyvale. We're going to be transferring that product over to this facility as we build this facility out. 50% of it is still under construction, but that's not stopping us from producing stacks in here today. What we do here is produce the fuel cell stack. 31 cells per stack. This stack is made up of two components. There's the interconnect, which is this metal plate where we screen print on seals, both on the fuel side and on the air side. When I say screen print on, it is just that. Just like a t-shirt printer, we're skiving ink and seal through a screen and depositing it on the substrate, so the interconnect. We also print on the cell. So this is the fuel cell. The white you see on the edge of the substrate is how we receive the raw material from multiple vendors. We screen print on multiple layers of anode, we flip it over, screen print on multiple layers of cathode. Then the margin that we retain from the printing process marries to the seal that we apply to the interconnect to make one layer. This is a one layer of a 31 layer fuel cell stack. So as we walk through the facility, I'm going to explain to you how we apply the ink to the cell, the seal to the interconnect, how we assemble this finished stack, and then finally how we assemble this stack into a finished column. So this tool is our automated interconnect print tool. And what we're doing here is applying the seal to the perimeter of the interconnect. We have the screen print process, and like I said, it's like a t-shirt printer. We're just skiving ink across the artwork. And right after we apply the seal, we inspect. So the light spectrum you see happening here is an inline automated inspection that we do at every single process step. This tool is 250 feet long. We print one layer, we inspect that layer, we dry it, inspect it again because a defect could manifest inside the dryer, and then we apply the next layer of seal. So with interconnect printing, we're applying the green seal to the edge and the donut holes. Through automation, the tool is identifying where the edge of the substrate's at, and there's a fiducial mark on the bottom of the screen to identify where the screen is at. The tool compares the two of them and adjusts the screen to be in the center of the interconnect, so we don't have to hard wipe the interconnect into position. This is our temperature humidity controlled fuel cell print room. And just like what you saw with the interconnect printing with the seal, we're applying ink to the substrate with the screen print process. We print it, we inspect it through that light spectrum you see behind me, and then it goes off to a dryer. We inspect it again before we apply the next layer of ink. There's multiple layers of anode, we flip the component over and apply multiple layers of cathode. Now leaving this room, these cells are dry to the touch, but the ink's not yet adhered to the substrate, so it has to go through a high temperature sintering process, which I'll show you in the next room. So here you can see the cells coming out of the dryer, going through another inline automated inspection. Pits and voids and bubbles, alignment, you can think of the might go wrong with the screen printing process for, we're checking. Then it goes through a print process. Much like the seal print process, this is a modular design tool, so if we did need to increase capacity, we could split the tool and insert another print head. After we print the green ink and the black ink on the cell, they go into these kilns for a high temperature multiple day bake. We put them in these ceramic firing rings to allow the circulation of that high temperature air, which is somewhere around 1,000 degrees C. So now we have the seal printed on the interconnect, the ink printed and centered on the cell. Now it goes into this tool named Automated Stack Assembly. And just like the name suggests, it assembles the stack for us. We have a cell, an interconnect, a cell, an interconnect, 31 cells per stack, and we have an end plate, which is a one-sided interconnect on either side of the stack. We have to temporarily hold the stack together with these metal clamps called ski bars because the green seal that we apply to the interconnect is also the glue that holds this stack together. And at this point, it's dry. So if we take these mechanical binders off, the stack would just fall apart. Here you can see the material handling robot behind me is assembling that stack, and the additional red, blue, green lights you see flashing are more quality inspection steps. We know that we process the components correctly because of all the points of assurance that we have inside the component processing tools. But here we want to make sure that we didn't rip a seal, break a cell from the last step to this step. We're also doing a topography scan of the seal to make sure there's no high points or low points. The output of this tool is a finished stack in clamps. The next process step is to fuse this stack together through another high temperature kiln. So this is the last process step in stack manufacturing. It's called stack sintering. And what we do is put the stacks into this tool with the metal clamps on the outside that I showed you in the previous tool with the dry seal. We put pneumatic pressure on the column. You can see the pneumatic cylinders at the top with the rods going into the kiln, putting a load of pressure on top of the stack. We lower the lid, heating up the stacks, and at a peak temperature, the seal liquefies, become a glass, and we use these pneumatic cylinders to compress the stacks down, squishing the seal. When it dries, it solidifies into the finished fuel cell stack. The stacks coming out of this tool are ready to produce electricity. We applied the seal to the interconnect, we applied the ink to the cell, we assembled the stack and baked it, and that's all that goes into this. The next process step is to assemble the stack into a bigger unit of measure, which is a column. This is our fuel cell stack, which produces just under 1 kilowatt of electricity, which isn't quite enough for our customers, so we need to stack these into columns. This is a column of 8 fuel cell stacks. 8 of these stacks go into one power module, a 50 kilowatt power module. This column is built not with just the individual stacks, but with fuel rails on the outside to deliver fuel to each of the individual stacks. So fuel comes up through the fuel rail, through a hollow splitter plate, delivering fuel to the hole in the top of the stack. The fuel flows across the face of the stack where the exhaust comes out, down, reclaim it, and bring it back up. This represents the different generations of stacks that we produce and columns that we produce. This older version, the 2.5, we still produce about 5% of our product is of this version, and that's because of field replacement units. So when this column finishes living its life out in the field, it comes back to us, and we do a process called singulation, where we separate the column, we harvest the cells out, grind that up into a powder, and sell this cell back to the tape cast vendor to make new cells. All the other components either get reclaimed or just reused as is. About 97% of this column gets recycled based on weight.